Welcome! In this explainer, we are diving deep into the science that makes next-gen manufacturing possible. We're going to peel back the curtain and see how engineers make absolutely sure that the advanced materials in everything from jet engines to supercars are strong, safe, and ready for the real world. So let's start with a wild idea. What if a material could talk? What if it could tell you its deepest secrets? How would you even listen? And if you could, what would it tell you about its strength or where it might fail? Well, it sounds like science fiction, but it turns out scientists have figured out a way to do just that. You see, the whole challenge starts with the materials themselves. We're not talking about a simple block of steel that behaves the same way no matter how you look at it. We're talking about composites. Think of them like a complex tapestry, woven together from different materials to create something incredibly strong. But that complexity, well, that's also what makes them such a puzzle for engineers. To really get a handle on this, you gotta understand three core challenges. First, there's anisotropy. That's a fancy word that just means its strength completely depends on which direction you're pulling or pushing. Then there's heterogeneity, which means it's a jumble of different materials, not one single pure thing. And finally, you have the form factor. Test samples aren't nice, neat blocks. They're often cut out of the final curved parts. And right there, you can see why the old ways of testing just fall flat. This whole anisotropy thing is a perfect example of the problem. Think about a piece of wood. It's super easy to split along the grain, right? But it's incredibly tough to break against it. Composites are exactly the same. A simple strength test done against the grain of the fibers could tell you it's weak, when in reality, it's incredibly strong in another direction. And you can imagine why getting that wrong could be catastrophic. So, with materials this complicated, how in the world do scientists get an accurate, reliable reading? How do they account for all these quirks? Well, they get the materials to talk to them, and the language they speak is the language of vibrations. And the solution, it's actually pretty brilliant. It's a technique called dynamic testing. The idea behind it is beautifully simple, really. You make a sample vibrate, and then you listen. I mean, really listen to how it responds. By decoding that response, you can understand its most fundamental properties, all without ever having to destroy it. It breaks down into this really precise three-step conversation. First, you ask the material a question by tapping it with a specific force. Second, you listen to its answer by measuring every little detail of how it vibrates. And third, you translate what it's telling you by comparing its vibrations to a computer model. So how do you actually ask these questions? Well, to get the full story, you don't just ask once. Scientists put the material through a kind of interrogation, a trio of stress tests designed to make it reveal all of its secrets. First up, we bend it. This is called flexion. You can kind of picture it like tapping a ruler on the edge of your desk and watching it wiggle. In the lab, they vibrate the sample back and forth just like that to see how stiff it is. This is absolutely crucial for something like an airplane wing, which has to flex under immense loads, but never, ever buckle. Second, we twist it. This test is called torsion. The material gets hit with these tiny, super fast rotational forces to measure how rigid it is. This is a huge deal for parts that experience incredible twisting forces. We're talking about the drive shaft in a race car or the massive blades on a wind turbine. And the third method? We stretch it. This is called extension. Now, this isn't about just pulling the material until it snaps. No, it's much more elegant. It's done dynamically, with vibrations, to see how the material behaves under tension. This is the kind of data you need to design suspension bridge cables or the body of a passenger jet. Okay, so we've bent it, twisted it, and stretched it. We've made it vibrate. So what? What do you actually get from all that? What does this so-called language of the material look like? And how do you turn a bunch of wiggles on a screen into solid, reliable engineering data? Well, this is what that language looks like. The results come out as a graph with these really sharp peaks. Each one of those peaks is what's called a resonance frequency. Think of it like a musical note. It's the exact pitch that the material just naturally wants to sing at when you get it vibrating. And this table here, this is basically our translator. It's how we turn that music into meaning. The actual pitch of the note, that resonance frequency, tells us exactly how stiff the material is. And then how quickly that note fades away, that's its bandwidth. And that reveals its damping, or in other words, how good it is at absorbing energy and vibration. And get this isn't some ballpark guess. This dynamic method is so good, it can pinpoint these properties with an error margin of just 5 to 7%. Now, that might not sound like a lot, but in fields like aerospace or high-performance auto racing, that level of precision is the absolute gold standard. It's the difference between good enough and mission critical. So, why do we go to all this trouble? Why does any of this really matter? Because this rigorous, detailed testing, it's not just a cool science experiment. It is the absolute bedrock of trust for every single thing we build with these incredible next-generation materials. I mean, listen to what the source material itself says here. It warns that testing off-axis or against the grain gives you mediocre results. In other words, if you cut corners, if you test it the wrong way, your data is basically useless. That's why this dynamic, nuanced approach is a total game changer for next-gen manufacturing. At the end of the day, that's what this is all about. Learning to speak this secret language of materials is what allows engineers to really push the limits. It's how they can design the future with total confidence, knowing that every single component is understood, it's validated, and it's trustworthy. The thing is, the materials of tomorrow are being invented in labs right now. And as they get even more complex, the big question is, how are we going to learn to speak their languages? Well, the answer is by continuing to refine these exact techniques, making sure that we will always have a way to listen to their secrets. And that's how we build our most ambitious dreams on a foundation of deep, unshakable truth.